Yeah. I see my open. Okay. Okay. Sharing. If you can see my sharing, you can
Yes,
tell
we
me.
can. Yes, we
Okay.
can.
So, so today we're going to start. So basically, I also forgot. I'll just touch a bit on periodic table, guys. You already know the periodic table. They're just the same things which you did in Zambia, and they just added some things which are very simple. And when you start doing your own, I believe you can understand it. Yeah. So I'll start with approximation the Slater. So you know that we're going to start with it. So before we look at this approximation the Slater, first you have to where does this approximation the Slater apply? So first we have to study the atoms plus their electrons. So when you are studying Rutherford, Bohr, Schrödinger, Broglie, those who are dealing with atoms with one electron, like hydrogen and hydrogenoids. The hydrogenoids, those who have lost almost all their electrons and they have only remained with one electron in the outermost shell. Then we found out that this equation of Schrödinger actually cannot really calculate the energy for an atom which has a lot of electrons. It was only used on hydrogen, the hydrogenoid, those things. So today, under approximation the Slater, we're going to look at the atoms are plus their electrons. You can say atoms with a lot of electrons. So it begins. Si l'atome contient plus d'électrons, les techniques actuelles de calculer ne permettent pas la intégration rigoureuse de l'équation Schrödinger. So we see that if an atom contains a lot of electrons, the equation of Schrödinger, the actual equation of Schrödinger is impossible to use it because one, the electrons, like it has a lot of electrons, and we have to use another way to calculate its energy, not using the equation of Schrödinger. So what is this way? So il faut utiliser the method d'approximation. So for us to calculate the energy, the charge effective, which we see, the charge effective of electrons, we have to calculate it using a method of approximation. Approximation is just something like you approximate something. So we see how this method of approximation was applied in respect to the atoms of which has a lot of electrons. So that's what we start basically, and it's something which is really simple basically. So the first thing which you have to note is that in the atome, dans l'atome du hydrogène et les ions hydrogenoides, les orbitales du même couche ou même énergie. So we see that in the atom of hydrogen and the ions hydrogenoid, the orbital do même couche or même energy. So the whole orbital of the same shell have the same energy, which depends on n, not which dépend de n, mais pas de r et de m. On dit que le niveau de énergie de gérer ou l'ordre de la digérescence est n2. So here basically what is saying that then in the atom of hydrogen and in the atom of hydrogenide, which has one electron in its atomic shell and which has one shell, the orbital, when I say the orbital, here should be thinking of the room which contains electrons. You say that each orbital represents the room and each room must have 2 electrons in it. So the orbital do même couche or même energy. So this orbital of the same couche has the same energy, and this energy depends on n. But it does not depend on L and M. So what do I mean when I say this? I made an example for you guys. Where is that example? Yeah, I made an example for you guys. So what do they mean if they say since you have to know that in the hydrogenide, so here I'm just want to bring up the difference between a hydrogenide and an atom which has a lot of electrons. So assume an hydrogenide. So an hydrogenide and hydrogen, they have got their level, like their shell level is Ln is equal to 1. And if n is equal to 1, for us to calculate their ordre de la digénérescence, n to the power 2, we know that the order of digénérescence is the formula which you use to calculate the number of orbitals. So for n is equal to 1, each number of orbitals, you calculate it by using n squared. This is the formula which you should know, and yeah, it's somehow for each one. That's how you calculate what its orbitals or its room, how many rooms it's going to have according to your n. So for hydrogen and hydrogenide, we know that our n is equal to 1. I hope you can see my diagram.
Yeah, we can see.
Yeah. So for hydrogenide, we see that and hydrogen n is equal to 1, and for us to calculate the ordre de la digérescence, the order of or the magnitude of the digérescence, which we use n2, which is just the same as the number of orbitals or the rooms which will contain only 2 electrons. So we know that where there's n, I will replace by 1. So 1 squared is equal to 1. So here, it means that donc, il y a un orbital or chambre, which is room. Et on sait que chambre orbital est occupée par 2 electrons. So we know that each room is occupied by 2 electrons, which will give us this, I'll just get this from your n squared, and each room is occupied by what? 2 electrons. So this is a formula which we use for us to calculate the number of electrons which will occupy that what orbital. So we see that 2n squared is equal to 1 squared, which will be which proves our theorem that it only has 2 electrons. So which is equal to 2 electrons, n is equal to 1. And you know that if n is equal to 1, your nombre secondaire est calculé par n minus 1, where n is the number which you have been given, and we have been given that n is equal to what? To 1, and so it means that your L, we just do 1 minus 1 is equal to 0. So your L is equal to 0, and your M for you to calculate the number of orbitals, we say that you after you find first to find your L, your number secondary, which is the subshells. After you find your L, then you find your M, and your M must be from negative L, which you have found is less or equal to M, which is less or equal to what? To L. And if you see here, we have L is equal to 0, which is neither a negative or a positive number. So your M will be is equal to 0. And if M is equal to 0, it means there is only what? One orbital. Yeah, it means that there is only one orbital. So that's why they say that in a hydrogen and hydrogen, right? Yeah, in a hydrogen and a hydrogen, right? It depends on N, which is the shell, but it doesn't depend on L and M because it only has one orbital. If you calculate the orbital, and this orbital, we say that if two electrons are in the same room, they'll have same energy, as we read, yeah, as we read here, that dans l'atome de hydrogène et les ions hydrogénides, les orbitales d'une même couche or même energy. So those which are found in the same room, they've got the same energy, mais pas the L, which are the same energy depend the N, mais pas the L and the M. So which depends on the shell. So the shell here is the one which plays a huge role, which when you move from one shell to another. But in this one, the L and the M doesn't play any role because there's L. Your answer is L is equal to what? When you calculate your L, you only have L is equal to 0 and the M is equal to 0, and you have one orbital, and that one doesn't really have an effect on the energy. So that's basically the niveau de energy. So digéré meaning they are constant, they are the same since they are moving in the same orbital, and you use this formula ordre de la digérescence, n to the power 2. So that's the formula. So that's for a hydrogenide. So for hydrogenide, really we never had, for hydrogenide and hydrogen, really never had any problem with that, since we know that the energy only depends on N. So we are just calculating for N is equal to 1, N is equal to 2, N is equal to 3, and we go on. Now the problem came in. Now we see the difference with an atom polyelectronic. An atom polyelectronic is simply, I simply means an atom with a lot of electrons. There was a problem here in such a way that dans un atome polyelectronique, l'énergie correspondante à chaque orbital dépendant à la fois de N et de R, c'est là une différence importante. La digénérescence de niveau de énergie est partiellement élevée. So what do I mean? Here, I mean in an atom polyelectronic, the energy corresponds at each orbital depend à la fois the N, the shell which you are in, and the L, the subshell which you are in. So it depends on the N and the L. So this is very important in such a way that the energy will be partially, it will be like, it will be increased. Level, it means increase, will be partially what? Increase. So what do I mean? I also made something, yeah, on that, so that, so what do I mean? I mean, for example, let's get N is equal to 2. When N is equal to 2, we know that there are two shells. N is equal to 1, then N is equal to 2. So when N is equal to 2, for us to calculate the ordre de digérescence, or the number of orbitals in simpler terms, we know that is N squared. So N is 2, so you have 2, so you have 2 squared. So if you have 2 squared, it means that you have 4 orbital. And when I say orbital, just think of a room. So we have got how many rooms? 4 rooms. And in these 4 rooms, we know that is each room must always have 2 electrons in it. So that's why I use this formula: 2 to the power n2 is equal to 2 times 2 to the power 2, which will give us the whole number of electrons, which will be what? 8 electrons. So the other thing which I want to clear, you might have questions: why each room must have 2 electrons? Each room must have 2 electrons in such a way that for it to reach its maximum, for it to reach its stability, it must have 2 electrons. One must be going up, one must be going down, which means you have a positive half and a positive, I can say a positive and a negative, which when you add them, they'll cancel out, they'll give you a 0, which is a stable. So you see, this is the formula which you must use when if you remember from from a secondary, this is the formula which you mostly use. You used to use when you are writing the configuration of something. You know that the first shell must have 2 electrons, the second shell must have 8, the third shell must have 18, so on, so on, so on. When you go on, that's the thing. So there's nothing different. There's nothing I'm adding here. I'm just trying to they just added some other information which I'm just trying to explain to you. So it means that each room, we have got 4 rooms. Each room has got 2 electrons, 2 electrons, 2 electrons, each room. Yeah. So which so if n is equal to 2, let's see the difference now. If n is equal to 2, and we know that when you're calculating your L, this is nombre secundar or the subshell, we say that 0 must be less or equal to L, where L must be less or equal to n negative 1. So when you're calculating your L, first you start from 0, which is L is equal to 0. Then after that, you get your 2 and you subtract by 1, which will be L is equal to 1. So most of the times you start from 0, L is equal to 1. That's the final, like you must always end L is equal to 1. When you have, for example, if I'm given n is equal to 3, I'll start from L is, I can start for this one, for you to better, I can start from L is equal to 3. So first I'll say 3 minus 1 is 2, L is equal to 2, L is equal to 1, L is equal to 0. So yeah, so most of the time you must always be going towards what? 0, I can say. So you subtract, you always go towards what? 0. So L is equal to 1 and L is equal to what? 0. So for L is equal to 0, how many orbitals does it have? It has, since we said 0 is neither a positive or a negative number, so we just write M is equal to 0, which is 1 orbital. And L is equal to 1, M, we said we're moving, for us to calculate, we're moving from negative L to positive L. So it will be negative 1, 0, 1, which will be 3 orbitals. So there's 1 for M is equal to 0, which has 1 orbital, which occupies 2 electrons. Then for L is equal to 1, which has what? 3 orbitals, which occupies how many electrons? 6 electrons. And when you add, actually, it will lead us to 8. So when you add this orbital, there's 1 orbital plus 3 orbital, it will give us 4 orbital, which is the same which you calculated here. You have seen. So this is the formula, the simplest formula. If you don't want to go into the pain of writing the M is equal to 0, M what you can write, you can just use this formula. You know the orbital and you know how many electrons should be in that room or in that orbital. So here, why I'm saying that N for Clusian atom, why I'm saying that N depends, why I'm saying that N depends on, why I'm saying that polyelectrons depends on N and depends on L. It depends on N in such a way that you are increasing the shell. So this one is evident, you are in shell 2, shell 1, shell 2. So yeah, this one is evident. Then for L is because here when you see, you have got 2 rooms. There's L is Yeah, sorry, let me continue. So yeah, so as I was saying, L is equal to 0, which is M is equal to 0. This is one orbital, which has, this is one room. I can say this is one separate room, which has one orbital. Then L is equal to 1, M is equal to -1, 0, 1. This is another room. This is, I can say, other rooms, which have got what? 3 rooms in it. So we see that the one L is equal to 0, the electrons which are in L is equal to 0 in this room, they have got the same energy. And the electrons which are in this room, they have got the same energy. So we see that it depends alpha N and alpha L. That's how it works when you deal with poly-electron atoms or atoms with a lot of electrons. That's how you go about it. So for N is equal to 3 is the same thing also. You find this orbital and you find this electron to be 18 electrons. So that's the difference between a hydrogenoid and a polyatomic. A polyatomic, it depends on number of shells and on L. But a hydrogenoid, since there's only one orbital, it only depends on number of shells, but it doesn't depend on L and M. That's what you should have in mind before we look at the approximation the Slater. So that was the difference, and that difference was very remarkable in such a way that Schrodinger's equation was somehow not really capable of calculating the energy of polyelectronic. So we'll see that this Slater formulates, Slater actually is a name of someone. He formulates a formula of how can you calculate this energy? How can you calculate the energy of atoms with a lot of electrons? How can you find their energy? So that's what we're going to see, and that's what we're going to study. So as I go, just follow me, and yeah, everything is actually just clear. So we're going to enter into our study.
Boss, I'm on the chair.
Yeah, you can ask a question.
Yes, our M and M represented.
M.
Yeah, L and M. What do they represent?
L represents a subshell. A subshell, when I say a subshell, is the way when we did, if you remember when we did our last lesson, we said that there are 4 quadratic numbers. There is principal N, principal L, principal M, and the principal the spin. So actually, N is the principal N, number principal L is the number of shells. So it's the shell itself. Then number secondary L, which you are asking about, is the subshells, or it describes the number of this subshell. Describe the number of electrons which must be occupied, the number of electrons which must be occupied in a shell. For example, shell 1 must have 2 electrons, shell 2 must have 8 electrons. So it describes the number of electrons which it must occupy. Then the M is the room, like when you go, it's like you start from the surface of the shell, then you are going deep, which you guys never, like secondary never did that. You start from the surface of the shell. So for in Zambia, we only know that there's a shell, which is N1, N2, N3, and there's a subshell, which is L, which we call L here, which can have 2 electrons, 8 electrons, 18 electrons, and so on. And when you go deep, we see that there's actually magnitude or orbital, which shows the orientation of these electrons, which is something which is very complex, which in simple ways, in simple terms, I can say is the rooms where these electrons must be occupied when you go deep. So these rooms must always occupy 2 electrons when you go under the the principle, the spin, which tells us that these rooms must occupy 2 electrons. So basically, it is something which opens the shell. You start from N, which you know already. You go to L, subshells, which you know also already. And you go to orbital, which a new information which is added for you, which actually are rooms, which shows the orientation. Then you go to spins, which is also a new something new which is added to you, which shows that electrons actually in each room, in each orbital, you must have 2 electrons. I don't know if it's clear.
Oui.
So basically, when I say L, M, N, don't get confused. So this N is shells, L is the number of electrons which must be found in the shells. Then M, the orbital, the room which you go deeper into the shell, and the spin is how the cell, the electrons, or how the electrons are moving, and how many electrons are there in the room. So that's what you should always get. Yeah. So knowing that, there's something which there's a definition. La dégénérescence est l'effet pour plusieurs états quantiques distincts de se trouver au même niveau d'énergie. So we see that the dégénérescence is the fact for many state quantic distinct, which are found on the same energy, which is the same thing which I'm from explaining. In N1 you have different number quantic. In N1 you have N, you have L, you have N, L, and M. Those in N2 the same thing. N, that's the number of shells. L, that's the electrons. And M, how they are oriented. Yeah. So now we're going to do approximation de Slater. So those like there, I was just trying to tell you the difference between electronic and the hydrogenide, which have 1 electron, or you can say mono-electronic, which has 1 electron. So approximation de Slater. Approximation de Slater basically is something which is those who have gone through is something which is very simple and something which is we don't even need to spend a lot of time on it. So the expression the energy potential du system contains the terms négatif due à l'attraction du noyau électron and the terms positive due à la repulsion des electrons. So we see that we all know that when you have an atom, the expression the energy potential du system contains the terms negative. So when you have this atom, the energy potential of a system, it contains a negative sign for, you know that a negative sign in such a way that there will be attraction between an electron and an ion, and the terms positive in which that there will be repulsion between, will be to repel, meaning to go apart. There will be repulsion between what electrons. So so what you should know here, basically, in simple words or in simple terms, in an electron, if you have an electron with a lot, if you have an atom, sorry, with a lot of shells and electrons, there will be 2 things which will be happening. One, there will be 2 things which will be happening. I want you to get me clearly. So there will be 2 things which you assume you have electrons. This is a polyatomic atom which has a lot of electrons. So there will be 2 things which will be happening. Let's assume this electron which is outer here. One, this electron will be attracted by the ion, but again, this electron which is outer here will be repelled by what? By its fellow electrons. Why will it repel? It will repel because electron is a negative charge, and the electron in the outer shell and the electron in the inner shell. In the inner shells, they've got the same charge, which is a negative charge. And when this charge, when same charges come together, you mean that you know that according to our physics, they repel. But a proton has an ion, or a nucleus has protons and neutrons. And we learned that neutrons have a charge neutral, and protons have a what? And protons have a charge positive. So the one which dominates is the charge positive. So we learned that our nucleus is positively charged in such a way that an electron will be attracted to a nucleus, and at the same time, an electron, which is outer shell, will be repelled by the electrons which are found in this shell and the electrons which are found in this the other shell. So yeah, so here when I say negative, I just mean the attraction of the ion and the electron. Then when I say positive, negative, when you see negative is when you get two different things, it's negative. So if you, for example, you add the positive and negative, like you get something which are different. That's a negative here, the sign negative, that's what is meaning here. Then the positive, it means I'm getting the same things which are the same, meaning electrons and electrons, which actually, if these electrons, they meet each other, they'll actually repel. So there's repulsion and the attraction at the same time. So this thing will really affect in terms of calculating our energy. That's where you see the name of approximation, the Slater. Like we only approximate, or when calculating this energy, we only do some approximation. So we see that the electron peripheric, which is the electron proof a la couche, external or denier, which I've already explained. So when I say electron peripheric, I mean an electron which is found at the outermost shell, which I've told you already. D'un atome est donc attiré par les noyaux, mais repoussé par les autres. So, electron peripheric d'un atome est donc attiré. Attiré, it means the atom is attracted by the noyau. Attiré is attracted, mais repoussé par les autres, which means it is repose is repelled by the other electrons, les autres electrons. That's all which you have to know. So when I'm talking about Slater, you should put that in mind. Two things, attraction and repulsion. Those are the things which you should put in mind so that you understand this Slater. And you see that this Slater thing is something which is very difficult, very easy in such a way that after you are done with it, you don't even need, if you know how to calculate, you know the principle. Each time when you're starting, just know the principle. If you know the principle, you never get wrong with anything. So, like l'approximation de Slater, or effet de Crane, assimiler la repulsion électronique à une diminution de charge du noyau. So, approximation de Slater, which is also called effet de Crane. So, you should, questions, this one I want to comment on. Sometimes they can use effect de Crane. They can't use approximation de Slater. Yeah, they say calculate the effect de Crane. Then you are confused. What's this? So when you are reading this, take note of effect de Crane. Also, it's very important. Sometimes they will just try to confuse you in asking questions. They will remove approximation de Slater, but they will just say calculate the effect de Crane of this, and that atom, and you'll be confused. So take note of that also. It usually comes. Assimiler la repulsion électronique à une diminution de charge du noyau. So approximation de Slater, it is assimilated to this repulsion electronic at the reducing of the charge of noyau. So we see in simple terms, I can say the approximation de Slater, which is assimilated to repulsion of electronic, is also assimilated to the diminution of the charge in such a way that when you are calculating the approximation of the Slater, you won't consider the electron which is at the outermost shell, the peripheric electron. You won't consider it. You only consider the electrons which are in the second shell and in the if I can explain with this diagram, since it will be easy. So when you're calculating approximation of the Slater, you won't consider this one. You only consider the electrons which are found in this shell and the electrons which are found in this shell. Those are the things, or those are the electrons which you consider. That's why they call it what the approximation the Slater, in such a way that you only calculate the electrons which are effective, or the electrons which are active at screening. We say screening, or yeah, which are active at screening this electron. So that's the energy which you calculate. And this energy, since the electron which is screened is only one, and the electrons which screen that electron, they are a lot. So when I calculate these energies for the electron for the second shell and the electron for the first shell, it means I have an approximation like of that energy. The outer shell, or actually I want to really, yeah, it will change something, but its change is solid in such a way that it won't really affect anything. That's why they say approximation the Slater. So approximation the Slater, you calculate the electron which are effective at shielding this other electron which is outside, which you won't even include when calculating, and you only include the electron which are inside, and these electrons which are inside the first shell and the second shell. That's what to include. So that's what this downward is saying here. The charged ion will definitely change, because one electron won't be considered which is in the outer shell. We only consider those. So meaning if the electrons, if an atom has, like for that one, has 11 electrons, you only calculate for 10 electrons. Yeah, we only calculate for 10 electrons, which makes that, which will somehow affect the charge, and which will somehow affect the charge of the ion, or which I can say in other terms, which will reduce the attraction, which will diminish the attraction between the electron which is outside the shell and the nucleus, which is what inside the shell, when diminishing the charge to ion. So this one, that's what you should know about. So you want to calculate for those which are effective at shielding the electron from the charge from the ion, meaning if they shield the attraction between these two, the charged ion and the electron in the outermost shell, will definitely reduce. I don't know if there's any question until there. If you have a question, you can ask. If no, we can go on. Is there anyone with any questions? Questions, guys, questions? We can continue or what?
We can continue.
Everything is okay?
Wait.
Okay, so yeah, so
I have a question.
yeah, can I ask you a question?
You are mentioning about the 2n squared as the formula. So you are saying we should just calculate for the first and the second shell. What if it has like more than 2 shells or more than 5 shells? You just still calculate for the first and the second.
No, actually, that one was an example. The N2 you can calculate for all the shells which they can give you. If they give you N1 to N infinity, use the same N squared. Just the same formula. So that one I'll just
All right.
yeah, I was just giving you an example for n is equal to 2, n. So if you see my examples, n is equal to 2, n is equal to 3. So you can go on using that formula. So just giving you that when you have n is equal to 2, meaning you also have the different subshells, nombre secondaire, and that's why I was just saying that if you have a lot of electrons, it depends on n and l. But that formula n squared can be used at the n number of shells which you are given. Yeah, so that's all. So we'll continue now. So we know that, so we say that approximation de Slater assimilé la repulsion électronique à une diminution de charge du noyon. So as I explained, this approximation of Slater, which is assimilated to the repulsion electronic, repulsion between electron and electron, it gives us the diminution, the charge of an ion, which I said they'll be screening the inner and outer shell, they'll be screening, and which means that if they screen it, if they create a barrier for it to reach or for it to be attracted to the ion, the attraction force between the outer electron and the ion is reduced, which affects definitely the attraction between the ion and the electron. That's why you see that as you go further from the ion, this is a concept which you had in Zambia. As you go further from the ion, the attraction force reduces in such a way that there are other electrons which are shielding this, and the radius is increasing, and its energy increases in such a way that when an electron is moving from inner shell to the outer shell, which we linked in Bohr, that the energy are always increasing. So it becomes more excited. So inner shell to outer shell, energy increases. Inner shell to the outer shell, attraction force reduces due to a reason of other electrons create as a barrier or as a screen for access, to allow it access to the ion, diminuing the charge. So we know that potential is equal to V, which we already calculated under Bohr, negative E squared over 4 pi epsilon R. This is potential energy. And the potential, the electron deviant, if you follow approximation de Slater, this potential of an energy, you add this charge. This is the charge effective. The charge effective E squared over 4 pi epsilon 0 times 1 over R, just the same as this one. So you know that the charge of Z must be less than Z because I've removed one electron, and the electron is very far from the nucleus. So yeah, so don't get confused. The E squared is simply this one. Potential is most related to the position of an electron and the distance from the radius, the distance from the nucleus to the shell. That's what it mostly relates. So don't get confused. So that's energy potential. So it just tells us that this the charge due ion must be less than the actual charge. Yeah, the charge due ion must be less than the actual charge, which after they did their mathematics, their calculation, they brought us. So for us, we'll be using this formula, this simple formula. This is the formula which we'll be using to calculate the charge effective. So the charge effective is equal to Z minus phi. This is phi, ij. So I'll explain. So ZA étoilé, c'est le charge nucléaire effective. So ZA étoilé is this is the charge of the nucleus which is effective. The charge of the nucleus which is effective in such a way that the charge which is acting on the electrons which is second shell and the electrons which is what in the third shell. This is charge effective. That's what we call the charge effective of an electron. If we don't consider the last shell which has one electron, we just remove one electron from it. So always we don't consider one electron. Yeah, if the last shell has, for example, if the last shell has 3 electrons, we only not consider one electron. That's what you should get in your mind. We only not consider one electron, and as we study, you know, as we do some examples, you understand these things more. So Z étoile is equal to charge nuclear effective, and Z is numeral atomic. Then phi ij, phi it represents the constant decay. So Z atomic is number of atomic number. Atomic number, you know, the number of protons for the same the element considered. Yeah, the element which are given. Then phi ij, phi is the constant decay, the electron. Then phi is the constant decay. Then the electron I, the electron I do or in J. So this is constant decay, meaning the shielding of which at I from electrons which are at J. See the, I cannot say see the English, but this is the French here. The electron is in a singular form, then the other electrons that are in the plural form. The way the electrons is in the plural form. So it means the screening, the shielding of one electron, I, from the electrons which are found inside, which are found in the second and the first shell. But also note that if I have the first shell, which has 2 electrons, the second shell, which has 8 electrons, and the third shell, which is the last shell, which has 4 electrons, note that I'll only remove for 1 electron. I won't calculate for 1 electron, but these are the electrons which are in the outermost shell. I'll calculate, I'll consider them. So most of the times you just remove 1 electron. Also consider that. That is very important, because if you go with the, I don't consider the outermost shell, actually you get it wrong. Sometimes you find the outermost shell has a lot of electrons. Actually it has 3 or 4 electrons or 5. How are we going to calculate? So for that one, if it has 5 electrons, we just remove 1, then we remove 4 electrons, so we calculate for the 4 electrons. So this is the formula for calculating the charge effective. So the charge effective is those electrons except for 1 electron. That's the charge effective which you'll be calculating. So we'll do some questions. So now the formula for NH total devient alors. So the formula for NH, you just have to know NH total is equal to summation Z étoile squared NH is 0 over N squared. So Z étoile, you see your Z which you find here. So for you to calculate energy, first you have to go through the formula and approximation, the strata, where you calculate the charge effective first. After calculate the charge effective first, you just replace here where Z squared. So Z, your answer which you have found, you just square it times E0 and N squared. So N, you should know that N is just in which shell are you in? Are you in the second shell or are you in the third shell? So I'll tell you all guys to know how to know that I'm dealing with the first shell, or I'm dealing with the second shell, or I'm dealing with the third shell. So I'll tell you all that, how to know about that. So which shell are you in? You have to know that for you to calculate. And energy E0, this is our famous. This is our famous value of negative 13.6. This is the one which we use always as energy. Energy is always constant. Since we said that according to Bohr, he opened the door for us, and he said to us that each shell has got a fixed energy, which the first shell is negative 13.6, the second shell negative 3.4, and so on and so on. So he opened a door for us, and if you consider a first shell, we know our energy is equal to negative 13.6 over n squared, where the first shell n is equal to 1, and when you square 1, it will always give you 1, which will give you negative 13.6, meaning that energy, you can calculate, that energy is the energy, you can, the energy in the first shell is what is I can say is the starting energy, and is the same because we are using what? We are using 1. There's no change in that energy. Unlike when I go to N2. N2 I'll be using 2 to the power 2, which will be 4, which will mean my energy will be I'll reduce my energy in such a way. But when I use n is equal to 1, my energy is never reduced. That's why they get that one negative 13.6. So 13.6, listen to me, is always the one which you place on energy when you're calculating under Bohr, when you're calculating Napotke, or in any energy level, whether n is equal to 2, whether n is equal to 3, whether n is equal to 4, your energy is always negative 13.6, which is very energy, which you place on A0. So this is how you calculate the energy total. So Z is the Z effective, which you calculate, which I will tell you how to calculate. Then E0, which is negative 13.6, our famous energy, which you know, negative 13.6 electron volt. Then N is the number of, in which shell are you exactly? That's N. I will also tell you how to know that I'm in this shell or in that shell. So here, yeah. So here, the values, the constant, the crane, or phi ij, Seleno star. So these values, the crane, they are always given to you. They are always constant. They are given to you. So don't you worry what I'm going to put on that or what. Magawa. If I said your name correctly, raise your hand.
Oh yes, I have a question on the constant energy, negative 13.60. You were saying that we are supposed to place it where there's A0. A0, isn't it an epsilon?
No. Easy, check the way I've written E here, and check the way I've written the E for epsilon. Epsilon is an E which is in a kind of 3. When you see an E which is in a kind of 3, that's an epsilon. Yeah, most of the times, like, yeah, it's normal to confuse them, but most of the times is when you see the E in form of 3, easier, I mean epsilon. But when you see I write E, the actual E, which is in a capital letter, na E0, this ufunga check 0 that this is for energy. I don't know if I'm clear. Mugaba. I don't know if I'm clear.
Yes,
the one who asked the question.
Yes, it's clear. Thank you.
Okay. So yeah, so basically it's very normal. Like, yeah, I actually like your question. It's very normal to confuse them because someone might, yeah, if you didn't ask that question, someone might have confused it with something. But you should always know that the epsilon thing is like a K3, which is if the switch is looking the other way around, then when I'm writing energy, it's the capital E. So thank you for that question, and yeah. So as I said, the constant decay is always given, is always constant in such a way that definitely you have to memorize it, you have to know it. sometimes they can't give you, sometimes they give you, sometimes they won't give you. So yeah, so you have, but it's something which is very simple. This is something which is actually very simple for you to memorize, and if you just know how to go about it, if you just know how to start from how to start, you won't have any problem. So I created something simple for you guys to help you in memorizing this thing. So actually, you don't need to memorize, you just have to know it. So now I want you to listen to me very carefully. Each shell, when you are writing a configuration, even though I haven't reached the configuration yet, each shell, when you are writing a configuration, it starts with toujours an S. S is just this is an S is a subshell. An S represents a subshell like SPDF. So don't get confused with this one. These ones, they just represent a subshell, like how many electrons are supposed to be in each subshell. So these SPDF, you don't need to be confused with them. So they're just things which they just represent the subshells, and you see something actually that these things you already knew them, like you knew them already, but they just wanted to. They just look you know, as you advance, you do new things, and these new things they also advance, but they're just the same things. They're just the same concept. I'll show you why I'm saying that these are just the same thing with the configuration which you did. I'll show you that, and I'll prove to you that, so that you know that you are doing just the same things, which is nothing different. Chemistry, there's nothing changing about chemistry, and you guys, you did a lot of things. So when you see an S, just know that it's a new shell. So for example, hydrogen has 1 electron in its outer shell. So it will be 1 SE, 1 NSE, outer shell. That's hydrogen. So if, for example, if you get hydrogen, if there's only one shell, the constant decay which you use is 0.30 if there's only one shell. So in calculating the effectiveness of hydrogen, you use its constant decay 0.30. But what happens if you have 2 shells? So I have 1s2. As I said earlier, for S represents a subshell, and for S to be full, it must have 2 electrons in this outermost shell for S to be full. So 1s2 is one shell, 2s1 is another shell. So this one will be, for 1s2, this one will be 0.85, they create the constant. Then 2s1, this create the constant will be 0.35. It's just the same when I write 1s2, 2s2, 2p4. I brought this in such a way that to show you that 1s2 is one shell on its own, 2s2, 2p4 is one shell on its own, unless I start with it. So there's 1s2, 2s2, 2p4. This is one shell on its own. Unless when I go to 3s, when I start with an S, that's when you begin another shell. So basically, that's how it is most of the time. Basically, that's how it is when you're writing a configuration. When you start with S, meaning that you have started, just assume you have started another. It's just like you have started another shell. So 1s2, it will be 0.85, 2s2, it will be 0.35. Then so you have seen, so it means if you have seen here, there's two, so mean they are just the same shell. That's why you are seeing 0.35, 0.35, just the same. So here just means the outer shell has got the 6 electrons in its outermost shell. then this one has 1 electron, which you lose completely. Yeah, that's basically what it implies. Then you have this one where you end at up to 3. So 1s2, 2s2. Then P, for it to be full, you have to have 6 electrons. Yeah, you have to know that one. For P to be full, you have to have 6 electrons. So when you move from S, P, D, F, the only secret which I can tell you is that you should know when S is to be full, you should know that it must have 2 electrons. Then when P is to be full, just add from those two electrons, just add the 4. I found that when I add 4, it actually gives me the number of electrons which each subatomic must have for it to be full. So I know that if S is 2, then the P which is following for it to be full is 6, then I go on. So it can have 6 or less. Yeah, it can have, a P can have 6 or less, then 2 can have 2 or less. Yeah, so P can never surpass 6, go to 10. So when you go to D is 6 plus 4 is what? Is 10. So D, for it to be maximum, for it to have all its electrons, it must have what? For it to be stable, to be full, it must have 10 electrons. So these are the things which you'll be doing. So let's try doing an exercise. So the same thing here, when I'm saying, when I have one shell, which I was saying, you only calculate using 0.30. When I have one shell, 2s and 2p, I'll start from one shell, it will be 0.85, 2s, 2p, it will be 0.35. When I have 1s, 2s, 2p, 3s, 3p, 1s, it will be 1. 2p, 2s, 2p, it will be 0.85. Then 3s, 3p, it will be 0.35. Then I continue. If I have 1s, 2s, 3p, 3s, 3p, and 3d, it means I'll have 1 on 1s, 2s, 2p, I have 1, 3s, 3p, I have 0.85, 3d, I have 0.35. So here I've just seen here, there will be, as you go down, there is just 1 which is coming, 1, 1, 1. Then the last part is just the same thing, 1, 1, 1. So the only thing which is different is the one which has one electron inside the shell. Yeah, like hydrogen, which is 0.30. But the other one is, you have seen the trend, 0.85, 0.30. Then when you come here, the S has 1, 0.85, 0.35, according to the electron configuration which you have written. So when you're given an atom first, try to write its electron configuration first. After writing its configuration first, you will know what to multiply with each electron. So an example here of helium. Helium has how many electrons? How many protons? 2. If it has 2 protons, it means it has what? 2 electrons. So its electron configuration, it will be 1s, the 1s2. Since we say that it's possible for S to have 2 electrons, so 1s2, meaning it only has what? 1 shell. When it has 1 shell, so it will be Z is equal to, we say that it is our formula Z is the number of protons minus constant screen times the number of electrons. So this constant screen times the number of what? Electrons. So here we see that it is 2 minus if you have seen here, there are 2 electrons. Then we said that when you're calculating constant, when you're calculating approximately the Slater, you don't consider 1 electron. So if you don't consider 1 electron, meaning you only remain from this 2 electron, we just subtract 1, you remain with 1 electron. So this is just why you have seen I've just written 0.30. Since I know that 1 times 0.30, it will just give me the same 0.30. So it will be 2 minus 0.30, which will give me 1.7. That's the charge effective. doesn't have units. So for carbon has a proton number 6, which means it has 6 electrons. So when feeding, I'll start 1s2, 2s2, 2p. Since 2 plus 2, it will be 4, meaning 4 minus 6, I'm remaining with how many electrons? 2 electrons. So it will be 2p2. So I know this one is a shell on this one, and this one is a shell on this one. So for this shell, I know I have 1s2 and 2s2p. So which means that I have 1s, 2s, 2p. So which means 1s will have 0.85, the number of electrons in 1s times 0.85, the number of electrons in 2s, 2p times 0.35, which will be 6, which is the proton number Z, minus how many electrons are in the first shell? There are 2 electrons, times 0.85 plus. Here we said we don't consider 1 electron, meaning if I remove, there's 2 plus 2, it will be 4. Then if I remove 1 electron, I'll remain with what? 3. So 3 times 0.35. So it will be 6 minus 2 times electron which are here. Then here I just remove 1. So I have 3 times 0.35, which will give me 3.28. Which definitely will, my energy, we said energy is equal to negative 13.6, which is the E0, times the Z squared, which is 3.28 squared, over the number, which shell are you in? So I said S defines the number of shells. So we are in the shell what? 2. So 2 squared. So which will give us negative 36.578 electron volts. So that's the simple way. That's how simply you calculate it. And there's nothing very difficult. You just have to know, if you know how to write the electron configuration of the element, the atom, it will be easy for you to calculate its charge effective. I don't know if it's clear until there. So this one, this table really don't, you just have to know that first shell is 0.35, then you have to know that these are the 0.85, 0.35, then as you increase the shell, you'll be adding the one, which the one will be going SC, such like you go like that, like that. That's what you have to know. I don't know if there is any question until there. Questions? It's clear?
Yes.
So those, like you have seen, Slater, principle of the Slater is something which is very simple in calculating those. You just don't consider 1 electron, that's all. And yeah, then you get it. Then your energy, you just replace, that's all. Then there's something which I want you to note, which we usually make a mistake in. I gave an example of lithium. Lithium has 3 protons. So this thing, you have to really note it. Such a way, when I write the configuration of lithium, there's 1s2, 2s1. And it will be 3 minus, you should minus, how many electrons are here? 2 times 0.85, then plus. Here, there's 1 electron is out of a shell. Meaning, if I don't consider that electron, it will be what? 0. But still there are 2 shells, but the last one I just lost what? Not lost, I can say not lost, but we don't consider 1 electron. So when you don't consider 1 electron, the second part will just be 0. So 0 times 0.35. So which will be, this one will give you 0, then this one 2 times 0.85, then which will be 3 minus 1.7, which will be equals to 1.3. When you multiply it, will give you then NH total Z times NH over N squared, which will be negative 13.6, which is energy times 1.3 squared minus. So it doesn't matter whether you have remained with 0 electrons here. whether you have like here, not actually 0 electron, I can say here, what you should always notice is that we are just, this electron is not lost or what, but it's just screened. So it means that still more, there are what? There are still 2 shells. That's what you should know. So there's 2 here, so it will be 2 to the square. So when you calculate, you'll find your energy negative 5.75 electron volt. That's the energy you should find. So here there's nothing really difficult, something which is really easy. Yeah, and I know this thing when you won't even find any difficulties when you pass through studying what, because it's something which is straightforward, and if you just know how to write configuration, you won't have any difficulties with this thing. So just know that un électron n'est pas considéré parce que on calcule ça active energy. So 1 electron is not what considered, because we calculate the active energy which is acting on this electron, which are except from this electron, which we only consider this what other electrons, as you saw in our calculations. So that's all about Slater's approximation, the Slater, and something which is really straightforward. Now we're going to go to structure électronique de l'atome. Structure électronique de l'atome. So structure électronique de l'atome is simply of you. How can you write? When I say structure électronique, is how do you write its electronic structure? Like just the same as the shell, the number of shells, like 1 shell, 2nd shell. How do you write? What things are you supposed to consider? Put in mind, we are dealing with an atom with a lot of what? Electrons now. So we are going to discuss about the structure électronique de l'atome with plusieurs electrons. That's what you should put in mind. And yeah, and basically just the same, like just the same with the one which like hydrogen, what, just the same. So this one I can say in simple terms, we're just talking about in general, because electron structure of hydrogen, you know that the neutron is on the middle, the electrons surrounding the neutron. So just the same. So I can say it's in general. So pour interpréter les propriétés des éléments par la structure de leur niveau d'énergie, et en particulier par la structure des niveaux périphériques, on a énoncé les règles de construction progressivement à partir de l'atome de hydrogène, le plus simple, jusqu'à l'élément de plus grand Z. On dit encore principe de construction. So, to interpret the properties of elements by their structure of their energy level and their structure of what and their structure of their outermost shells, we have to formulate a way of drawing an atom from a most simple atom of hydrogen to an atom which has what? A lot of electrons. So when you say pour interpréter la propriété de l'élément par la structure de leur niveau de energy. Niveau de energy simply means for me to interpret that these electrons has niveau de energy, as we said earlier, to interpret its number of shells, and on particular to interpret what? The structure of the shell, the outside shell, like how many electrons must have the outside shell, all that. So for us to interpret all that about an atom, we have to follow some rules. We have to follow some rules of construction, which we have to put in mind in terms of drawing a configuration, in terms of drawing this structure, the atom structure, in terms of drawing this a card, in terms of drawing, like in terms of a lot of things, you have to observe somewhat rules, and these rules starts from these rules. It will compromise, or it will compromise from the atom of hydrogen, which is simple, you know, 1 electron, to the atom which is the Pru grand Z, which has got in simpler terms a lot of electrons. So this is what we call, so the start of these things is what we call principle de construction. So what do you consider if we are writing structure electronic del atom? What do we consider? They can be electron configuration, it can be the number of shells, it can be the cut meaning each room, like this one, the cut, laser cut, yeah, each room, how many electron must it have? So what principles should we follow, or what principle the construction should do for? So the first principle is principle de exclusion de Pauli. Dans un atome, des électrons ne peuvent avoir les 4 nombres quantiques égaux. So you know that in an atom, 2 electrons can never have their 4 nombres quantiques égales. What do I mean? We have N, principle L, secondary, subshell, the magnitude, principal number, the magnitude, principal M, and we have the spin. So we have this 4 number which describe an atom. So he's saying that according to Paul, he said that among these 4 numbers, among these 4 quantic numbers, an electron cannot have all of them equal. 2 electrons cannot have all of them equal, which are in the same room. When 2 electrons are in the same room, they cannot have everything equal in such a way that we know already the difference. There's a difference in spin in such a way that one will be spinning the clockwise direction, the other one will be spinning the anti-clockwise direction. So that was Pauli. That was the principle of the Pauli. So the principle of the Pauli was saying, when you are writing a gas quantique, or when you're writing, they'll ask you present this in a cat quantique, or simply they mean something like present this in this orbital or in this room. So they'll ask you questions or that. I'll definitely, if I find any question, I think I have some questions, I'll give you guys if I find any questions. So you should know that an atom, in an atom, 2 electrons cannot have all the number quantique equal. It can have the N equal, the L equal, the M equal, but one must be different. Most of the times it's the spin which is different if you have 2 electrons which are equal. So il est différent en moins par le spin, which is, you have a spin positive, which is an electron which is moving postward, which is arrow which is pointing up, and the spin negative, which is an electron which is moving anti-clockwise, which is an arrow pointing down. And these 2 spins, they are what? They are opposing, they are not equal. So for them to be equal, the spins, both of them, they're supposed to look up, but one is looking up, the other one is looking down. So that's the principle of inclusion de Pauli. So this principle should always follow it when you are taught to write the ICAT, when you are taught to write presenting it in this a card in this room. That's the principle which you must always follow. Yeah, so that one is for the first one. That one is for the first one, which you should always follow. Then for the second one, we'll go to the principle of stability. So principle of stability is something which is also something which is very simple. Yeah, principle of stability. Yeah, so yeah, principle of stability is something which is what? Very simple. So most of the times for principle the inclusion of the poly, just to add on, you only draw it in these rooms when they have asked you a question to draw it in terms of a cat, a car. Yeah, a card, E-C-A-R-T. It's just mean card in English. So you find those, like you find, I'll try looking for a question for you guys. Then principle of stability. Principle of stability is something which is actually very simple. Yeah. So from there, I don't know if you are following me. Before.
Yes.
No. You just repeating the principle of stability.
No, I haven't said anything on principle of stability. So that's when I'm saying, yeah. So under principle of stability, à la tête fondamentale, le remplissage progressif des couches s'effectue de manière à l'atome l'énergie totale minimale, donc une stabilité maximum consequence. So this is the theme which I explained already when we are looking at Slater, when we are looking at the polyelectronics in general, in particular. So when I say à la tête fondamentale, the reprécise progressive des couches s'effectue de manière à l'atome d'énergie totale minimale, donc une stability maximum consequence. So what it means here, when I'm given an atom, when I'm given an element, when I'm given an element, for example, I say oxygen. Oxygen has got proton number of 8, which means it has got 8 electrons. So when I'm feeding, for me, for stability, when I'm feeding this electron of hydrogen, the first shell must have 2 electrons. Then the second shell, since hydrogen has 8 electrons, so 2 minus 8, you remain with what? You remain with the 6. So 2 electrons in the first shell, then the second shell, since the second shell can occupy 8 electrons for it to be stable, and you have 6, which is less than 8. So you put a 6. So here I'm just trying to tell you that when you are feeding, according to stability, principle of stability, when you have been given an atom, when you are feeding its energy shells, you have to start from a niveau, the energy total minimum. You have to start where the energy, or where the niveau the energy, which means the N is low, where N is equal to what? To 1, basically. So I'll start from N. I feel it first until it becomes stable, and I know that N, for it to be stable, must have 2 electrons. Then that's when I go. So you go in stages. So you feel one, you feel the other one. Yeah, that's how you go. And according to stability, for something to have a stability, it means it must have full electrons. Like it must have each shell, for example, which one? For example, if you get noble gases, principle of the stability states that when you get noble gases, you know that noble gases, all the shells are full. The N, for example, argon, if I'm not mistaken, has a proton number of 10. Yeah, if I'm not mistaken, argon. So when you get argon, it has 2 electrons in its first shell, and in the outer shell it has what? 8 electrons, meaning it's following this principle of stability. So when I say principle of stability, it's the principle which allows me, or which tells me how I can know that this atom is stable or not. So what formula do I use to know that this atom is stable or not? If you remember our formula, we said that each orbital must have 2 electrons, then N2. So for me to know that it's stable, I know that N1, if I only have one shell, I must have L is equal to 0 and N is equal to 0, which will give me what? One orbital, and which I said is one room. And in this one room, for it to be stable, for this room to be full, so I will just do, it must occupy 2 electrons. So 2 times 1 squared, which will give me, which will give me 2 electrons. 2 times 1 squared, 1 is N, which will give me 2 electrons. So meaning this orbital is what? Full. So the first shell is full. Then the second shell, we know that it has L is equal to 0, M is equal to 0. That's for L is equal to 0. Then there's also L is equal to 1, M is equal to -1, 0, 1. So we know that for this one, for the S, that's what I was saying. Each shell starts with an S because L is equal to 0. So for an S, I know that it must have 2 electrons as we had already calculated. If I have L is equal to 0, M is equal to 0, if it has one orbital, for it to be full, it must have 2 electrons. Then for this one to be full, actually I must do, you have seen the, for this one to be full, it has 1, 2, 3, which means it has how many orbitals? Has 3 orbitals. So for it to be full, I know that each orbital must, or each room, when I say each orbital, you should know that I mean room. Each room must have 2 electrons. So there are 3 rooms, 1, 2, 3. So meaning they have 6 electrons. So yeah, so this one has 2 electrons, and this one has 6 electrons. So when I add these electrons together, for my N2 to be full, it must have 8 electrons, which you can prove by this formula, 2 to N power, where N is the shell, the shell where you are in, which is 2 to the power 2, which is 2 times 2 to the power 2 is equal to 8 electrons, which is proven also by writing this formula. So for you to know that this atom is stable, you have to use this formula for you to know how many electrons must each shell have. So the first shell, 2 electrons. The second shell, 8 electrons. The third shell, we know that 3 to the power 2 is 9. So 2 times 3, 18 electrons. So, you go on and you go on. These are the things which you did under senior secondary. So these are the things which you know already. That's under principle de stabilité. I don't know if I'm clear under principle de stabilité. I don't know if I'm clear.
It's clear.
Okay. Yeah, so that's under principle de stabilité. So these are the things which you already know. Then règle de Hooke. What does règle de Hooke say? Règle de Hooke say lorsque toutes les orbitales du même sous-couche contiennent un électron et seulement lorsque ce demi-repoussage est réalisé. Le repoussage c'est poursuite par la formation de doublets. What do they mean? They mean when you are filling an orbital, for example, an s orbital, we know that it has one room. It will be, if it is an s orbital, we know that it has one room, so it will be just up and down. Yeah, but there are cases where we have the p orbital. The p orbital, we say that its maximum for it to be full, it must have 6 electrons. So for you to find this room, you just divide that 6 electrons by 2. Yeah, you find this room easily. Like that's how. So an orbital P, for it to it must occupy 2 electrons, 6 electrons, and you know that each room must have what? 2 electrons. So meaning you just divide 6 divide by 2. So meaning it must have 3 rooms. So how does this Legendre would say? Yeah, how does this Legendre the would say? It says, first of all, tous les orbitales du même sous-couche must contain, so all the orbitals of the same couche must have first 1 electron. Then after you have filled with them 1 electron, that's when you start now filling, that's now you start filling the opposite electron. So there'll be, each room first you put 1, 1, 1, 1. Yeah, I think I drew something for you guys to explain it. Yeah, so this one under principle of the stability just showing that N1 must have 2 electrons for it to be stable. N2, if you calculate, must have 8 electrons. N3, if you calculate, must have 18 electrons. That's the thing which I talked about. Yeah, so here which you can just represent it here. Just here, don't when you come under configuration, don't confuse this. Here I'm just trying to show you the similarities between. So here I'm just talking. I think I never talked about. So here is principle of stability. Don't confuse anything. So principle of stability. I'm just trying for it to be stable. The first shell must have 2 electrons. The second shell must have 8 electrons. The third shell must have, if you see, 6 plus 2 plus 6 is what? 8 plus 10 is what? 18. So you see, this is the same thing from the thing which you did in Zambia. The first shell 2, the second 8, the third, since you said each word begins at S. So this one, I just told you that you should take note that when you're writing this configuration, there will be, we don't usually write 3S, 3P, then 3D. No. Well, after 3P come 4S and 3D. You then I'll tell you why is that and why do we do that when you're writing configuration. Here I'll just trying to show you that just the same thing. So under Legendre, the wood. So what I was trying to show you is when you are feeding under Legendre wood, I want you to follow me. When you are feeding under Legendre wood, you have 1s2. 1s2 I'll fill up and down since there are 2. 2s2 I'll fill up and down, yeah, since there are 2. Then 2p6. So for 2p6, first of all, according to Legendre, the wood, it says first to fill in, the first step you fill in up, up, up. Then after filling in the first step, the second step now, that's when you can't fill the opposite one. So don't ever try wafaka electron then you make it full. No. First fill it in, then after filling it in, find, since these guys are single, so find their appropriate couples, so that appropriate partners. These are the partners which are coming here now. Now they are full. Now they have now they have partners. So what usually you place them as single guys. Then after that you find their partners, and they are full. Then there's some circumstances where you see that after feeding, I don't know if I have any here. Yeah, like for this one, you have 1 down, up, down, 6, up, down, up, down, up, down, up, down. See this one here, the last one. The last one, you know that D must have 10 electrons for it to be full in D. So it must have what? 5 rooms if you divide 10 by 2. So This is room 1, room 2, room 3, room 4, room 5. So I'll start putting 1, 2, 3, 4, 5. I'll put 5, but there are 6 electrons, meaning 1 down here. So it means when I'm feeding, you first start with the up in each room, and after that, that's when you go down. If you have that's how you feel most of the time. That's how you feel. So for this one, 2, you know that it has only one. It only has one orbiter. So it's so this one. So that under D, you have this guy who has a partner, and he's already has a partner, and you have these guys which are célibataire, which are still single. So that's how you do it. And you see that according to this one, according there, you see there are 1, 2, 3, 4. So these guys will need 4 other electrons for them to be full, for them to be stable. So you see that this atom, it's not stable generally. For it to be stable, there must be the up and the down, the up and the down, the up. Now they are just up, up, up. So meaning it's not stable. Yeah, so that's the regular what, which is something which is not really difficult, something which is simple. So you should always know that you should always put the electron, the first put electron célibataire, which electron single. After putting electron single, you find this partner. Then you according to the number of electrons which you have, if you have 6 electrons, that's how you go about it. And you put this what according. So if you count, to be 1, 2, 3, 4, 5, 6. So that's like that. If you are drawing according to the way. Like that. I don't know if I'm clear until there, or if you have any question. And the hood. So first, so if you see here, les représages se produisent par la formation des doublets. Les demi-représages sont dits correspondraient à des electrons célibataires or non-apparent. So célibataire just means single. These are electrons which are what? Single, they don't have what? First, you do the demi-représages of single electron. That's when you put this opposite. That's according to Legre-de-Wood. I don't know if, is it clear, or I should repeat?
C'est clair.
It's clear. So yeah, so basically that's how you do with it. So most of the time they will tell you how to write, they'll ask you how to write, and that's what you should do. You should always put in mind this regular is really important actually, because for example, if you put in up down, you will find that the other room won't have any electron left. So you have to put them single first, then after that, that's when you can add their partners. Yeah, if it's 6 or it's 5, then you see that there are some who remain single, but you will know how to, you know, like you know how to what if for example, if there's gaining and losing of electrons, those things, for them, maybe for them to what, you have to gain electron from another proton for you to have a full, or for you to have a stable atom. So that's what happens when you gain, meaning one of these single what will gain an electron, and it will be, for example, it will be down here. Yeah, you can fill in this one. Then if this one also gains, you fill in this one. That's where the stability now comes in. Yeah. So that's all. So regular the Kleshkovsky. So this regular is the regular which tells us definitely on how to calculate the number of shells, how to calculate how to do the electron configuration. So This is the rule which tells us of how to calculate electron configuration. So if basically you know how to, if you know how to interpret this rule of Kleshkovsky, you will know how to write. You will never find any difficulties in writing electron configuration of any atom. Like you will know how to write and you will know how to follow. So, à partir d'une certaine énergie, les sous-couches du niveau se chevauchent avec les sous-couches des niveaux différents. So we see that à partir de certain energy, starting from a certain energy, which when I say certain energy, I basically mean the energy level, like the energy niveau, the n is equal to 1, n is equal to 2. We see that there is overlapping of a what? Of a sub-push. What do they mean? They mean, for example, if n1 is equal to 1s, n2 is equal to 2s, 2p. So you see n1 is 1s, n2, 2s, 2p. So there is overlapping. So it will be 1s, 2s, 2p, then 1s, 2s, 2p, 3s, 3p, 3d. That's for n is equal to 3. So there is overlapping of the sub-couche. So that's how you go. So first couche is 1s. The second couche, you must know it must have 2s, 2p, but most of the times you start on 1s, 2s, 2p. Then the third shell must have 3s, 3p, 3d, which you start from 1s, 2s, 2p, 3s, 3p, 3d. Then the fourth shell, when you're adding configuration, yeah, see the fourth shell will be 4s, 4p, 4d, 4f. Since you know that for you to reach the fourth shell, you have to move from the first shell 1s, the second shell 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Then you go on, n5 must have 5s, 5p, 5d, 5f, 5g. So you have seen from 1s it goes to 2p, from 2p it goes to d, from d it goes to f. There's overlapping. From f it goes to g, and g it was supposed to go to, if you go on, there's h, but e, in our case we're only limited on g. Most of the times we only reach f, don't usually reach the g. So most cases we reach on f. So how do you calculate its electron configuration? So these are the things which I want you to consider. These are the things which I want you to consider. In order to calculate the electron, in order to write the electron configuration of an electron, first of all, you have to consider ordre de reprécise the orbital atomic. So first of all, you have to consider on remplit les orbitales à n plus l croissant. So we fill the orbitals which have n plus l, which is what? Increasing. How do I? What do I mean? As you if you see here, you have the L is equal to 0 here. When you see L is equal to 1, so S we know that L is equal to 0. P we know that L is equal to 1. D we know that L is equal to 2. F we know that L is equal to 3. G we know that L is equal to what? 4. So now in S you know that if L is equal to 0, 1 orbital, L is equal to 1, -1, 0, 1, 3 orbital, to 2, -2, -1, 0, 1, 2, 5 orbital. So that's we know. So we know our orbital. So how do you write this configuration? So when you're writing configuration, we'll calculate n plus l croissant. We'll start writing this is the electron configuration in such a way that L plus L must be giving you an increase. So what you do is, for you to know that am I supposed to start with 1s or 2s? So for you to know that which one am I supposed to start, is it either 1s or 2s? What you do is, if n is equal to 1, you say 1 plus 0, it will give you 1 plus 0, it will give you 1. So you say that you see that it is 1s. So you begin with this one because this one is 1s is what? 1s is actually smaller. When you add 1 plus 0, it's smaller with this one. When I have n2, 2 plus 0, it will give me what? 2s. Then 2 plus 1, it will give me what? 3. Then now that's where the problem comes in. 2 plus 1, it gives me 3. So here the question is, should I start with 2p or 3s? Since I know that 3 plus 0, it gives me 3 also, and 2 plus 1, it gives me 3. So which one should I start feeding, and which one when I'm drawing my configuration? So here, in case d'égalité, on remplit d'abord la couche de plus petite n. So in case there's an égalité, in case there's an égalité between n plus L, if there's an égalité when you do n plus L, we first fill the shell which has what? Which has less, which is less in terms of n. For example, here first we said 1 is equal to 0, so 1 plus 0 is 1s, which is 2 plus 0, we know that is 2s. So I first fill this one. After I fill this one, 2 plus 0, I will fill this one. I know it's 2s, which is less than 3. Then 2 plus 1 is 3, but n for this shell is equal to 2, and n for this shell is equal to 3. So I'll first fill this shell where n is equal to 2, and 2 is less than 3. So I know that 2 plus 1 is 3, so I'll fill this one 2p first, since this energy level is lesser than this energy level. Then from there, that's when I go to 3. 3 plus 0, I have 3s. Then 3 plus 1, I have 4, and I know that there's 4 also. Then 3 plus 2, I have 5. So here now, there's a problem again in my filling. So here we have discovered that I fill this one because it's less than this one. I fill this one because it's less than this one. And this one, even though it's equal with this one, but the energy level is less than this one. So I'll fill this one, which will be followed. Then after I fill this one, I go to this one, which is 3 plus 0. I fill this one. Then 3 plus 1, it gives me 4. But I know that 3 is less than the 4s here, which is 4 plus 0. It is 4s. So I'll fill the 3p. Now the problem comes in. 3 plus d, we said d corresponds to L is equal to 2. So when you say 3 plus 2, 3 plus 2, it gives you 5. So how do you do with this one? Like, this one, we know that 3d is less than 4s, which is 4 plus 0, if it corresponds to L, S corresponds to LS. So what you do is, according to what we said, we fill according to the what consoles, like how is increasing, when you add n plus L, how is increasing n plus L, and we know that 4s is less than 3d, since d corresponds to 2. So I'll begin with what 4s first. Then after I write 4s, that's when I go to 3d. So I know that 3d plus 2 is 5, and the 4p plus 1, since p corresponds to L is equal to 1, is equal to 5. So it will be 4s, 3d, then 4p plus 1, it will give me what? 5, which will give me 4p. So what I mean is 1s, 2s, 2p. So when you're writing, first you start in 1s cell, 2s, 2p, then you go to 3s, 3p, then you go to 4s. Since 4s is L corresponds to 0, you know that 4 plus 0, it will give you 4. Then 3d, d corresponds to 2, 3 plus 2, it will give you 5. So that's why 4s comes first and 3d comes second. Then 4p also gives you 5, but you know that 4p, n4 is greater than n3, so you start with 3d. Then you continue with the same way. Then you say 4f, L corresponds to what? To 3. Then 4 plus 3 to gives you what? No, on D, we're on D. D, 4D, D correspond to 2. Then 4 plus 2 to give you what? 6. Then yeah, 4D is 2. Then 4 plus 2 it will give you 6. But you know that you have got 5 here. If you see the 5 here, you know that 5 plus S here, which is 0, which corresponds to 0 to give you 5, and the 4 plus 2, you know that it gives you 6. So which one you fill first? You fill first the 5S. Then after the 5S, that's when you go to the 4D, which gives you 6 plus 2. Then after you fill the 4D, which gives you 6, then you go to the 5P. You know that P L is equal to 1, correspond to L is equal to 1. So 5 plus 1 is 6. So you fill the 5P. So that's how you go basically. So that's how you go basically. So you find that it will be 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D, 5P, then 6S, 4F, 5D, 6P, 7S, 5F, 6D, 7P. So when you continue, that's how you do most of the times. That's how you do. So you should always know that this is something which you should know. When you are writing this configuration, you should always put in mind you are adding L plus N, and you fill according to the consoles, the increasing of L, N plus L. So for S shell, L is equal to 0. It starts from 0. For the P shell, you should know this one, L is equal to 1. For the D shell, L is equal to 2. And for the F shell, L is equal to 3. These are the things which you are supposed to know. Yeah, I don't know if it's okay up to there. So you should know that S is equal to 2 maximum, P is equal to 6, D is equal to 10, F is equal to 14. So this is a fixed. X must always be equal to 2, P must always be equal to 6, D must always be equal to 10, and F must always be equal to 4 for it to attain this maximum. So it can be equal to 2 or less than, equal to 6 or less than, equal to 10 or less than, equal to 14 or less than, for it to have an electron share which is full. Yeah, so I don't know if it's okay until there.
Where is it clear?
It's clear. So when you're writing these things, don't usually get confused on them. You just have to, if you have the N and L formula in your head, N is the number principal, L is the number secondary, which you know how to calculate for. N is equal to 1 is N minus 1 is L is equal to 0 under S. Then N is equal to 2, N minus 1, L is equal to 1 under P. So you have to just to know it in your head, and you never find any difficulties in writing the electron configuration of any atom which you are given. So most of the times they just end on D. Yeah, that's where they end. So there's this one example, ion, which has 26 electrons, 26 protons, which is the same of electron. So the first, I know that it will be 1s squared, 2s squared, 2p6. So this they have altogether 8 plus 2, 10. So I'm remaining with 10 minus 26, I'm remaining with 16 electron. Then I continue 3s2, 3p6, 4s2, this whole thing is 10. So 10 plus 10 is 20. And if 20, I'm remaining with 6 electrons. Then after 4s, I'll go to 3d6. Then I'm done. So I said D can have, its maximum is must be 10. Cannot bypass 10, 10 or less. That's its maximum. So in terms of a cut, you just write up, down, up, down. For 1s2 is up, down. For 2s2, up, down. For 2p6, up, 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 down, down, down. Yakwana 6. 3s2, up, down. 3p6, up, 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 down, down, down. Yakwana. And 4s2, up, down. 3d6, up, up, up first. Then after 5, then down. For it to have 6 electrons. So if you're writing the cut, don't if you are taught to present the cut, don't even think of how am I going to write. Just know that S to be full must have 2. So you just divide by for you to write, divide by 2. It will be 1 a cut, and in each card there are 2 you must have 2 electrons up and down. Then for P, for it to be full, is 6, maximum is 6. That 6 just divide by 2, meaning it has 3 boxes, 1, 2, 3 boxes for it. Then you fill in those boxes. So don't really panic much on how to draw the card. These things are actually simple. Yeah. So those are things according to electron configuration. And if you just know how to do those things, you will never find any problem. Whether they give you any any atom, you can calculate easily and you won't find any problem. Then periodic table, I said you won't do it. Yeah, periodic table, I said you won't do it. But there's something which is important, just a small part, yeah, which is important, but won't really do it. This actually, when I say S, P, D, and F, these actually the blocks of the periodic table, which yeah, so under periodic table, yeah, under periodic table, yeah, under periodic table, there's just small things which I want to tell you guys. There's where we call an S block, there's a P block, and there's what we call F block. So there's an S, P, and D, F block, and D block. So these things actually is there are things which are very simple. You know. So, can you see my sharing?
Yes.
Okay. So under periodic table, I'll just tell you the S block, the P block, and the where is the S block? Where is the P block? Yeah, this is our periodic table. So under our periodic table, we have IA. IA is called S block, and 2IA is called what? So elements of group 1 and elements of group 2, they are called S block. I'll tell you why they are called S block. So right now, just listen to me. So elements of group 1 and group 2, they are called S block. Then the elements which are found here, the transition metals which are found in the middle here, they are called the D block. Then the ones which are found here, the non-metals which are found here, they are called the what? The P block. Then these which are down here, which like they are removed, they are down here, they are called the F block. So these in simple terms, I can say group 1 and group 2, they are called S block. The middle part is called the D block, and the non-metals are called the P block. Why do we call them S block, D block, and P block? The reason is, and the down part, why do we call them F block? So the reason is, elements in the first shell, they only end, all of them, they end with S. They end with, when you're writing their configuration, they end with, it can be 2S, then 3S, 4S, it depends. So all of them, they end with an S for group 1 and group 2. Then for transitional metals, all of them, they end with a D when you write this their configuration. Then the non-metals, all of them, they end with a P when you write their configuration. So how they are ending, that's the block which they belong to. That's what you should put in mind. So for example, I did an example. So this is just group 1 and group 2. I got sodium, which is in group 1, and the potassium, which is in group 2. So if you see this electron configuration, there's 1s2, 2s2, 2p6, 3s1. So this one is ending in S, which is S block. So I can ask in which block does sodium belong to? When you write this configuration, by just seeing how the last shell is represented, you know it's block. Then for group 2 elements, you know there's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. We see that it's also ending in what? In S for potassium, which is in group 2. So it is what? S block. So we see group 1 and group 2, they represent S block. So this is how you find. Sometimes they when they say which element belongs to S block, meaning which one ends with, when you write this configuration, it ends with what? S. Then sorry, I made the mistake. These are group 1 elements, those which ends with 1 electron. They are group 1 elements. Then I gave you for group 2 elements, there's potassium, calcium, and magnesium, which ends in 4s2, 3s2. So 3s2 and 4s2, these are group 2 elements. So if you see here, they end in S, they end in S. So you have group 1 and group 2 ending in S. Then P block, I got different from group 3 to group 8. Group 3, 4, 5, 6, 7, 8. So I got from group 3 to 8. And you see that all of them, they end in P. For aluminum, which is in group 3, which has a proton number of 13, you see that it ends in P1. For silicious, it ends in P2. For phosphorus, it ends in P3, and sulfur, it ends in what? P4. So you see that when I say P block, something which is not different or something which is not confusing, just I mean that the end, when you write this electron configuration, it's supposed to end in what? Supposed to end in P. Then F is similar also. For F, is D block is group 3B to group 2B. This one, we see these represent the elements which are in the middle. So yeah, you can try calculating, try writing the configuration. You find that they always end in D also. They always end in D. So under what? Under periodic table, I think that's the most important thing which you have to know. I don't know if I'm clear.
Yes, you're clear.
So, yeah, so these things when you read them, you see that they are very simple. You just understand them like there and then, these things. So there's no need of us doing these things. Since we are fighting with time, I don't know if it's okay with you. I continue. Because now we're just doing the last one, liaison chimique. Because maybe you are tired or what. This is the last, I'm done with this one, then you are done with the whole topic of liaison chimique, which can only take me about 30 minutes. So.
You can finish it.
I can finish?
Yeah, I don't know about.
Yeah, so guys, under the liaison chimique, also a lot of question comes from the liaison chimique also. Yeah, this is the topic which it confused some people, and but it's something which is, you see that it's something which is very simple, and something which you guys, you are already familiar with. So we'll begin. La notion de molécule est un des concepts fondamentaux de la chimie. Une molécule est un groupe d'atomes qui conservent lors des changements d'état physique. So la notion, it also means la connaissance or the knowledge of molecules is the concept fundamental. It is a fundamental concept of chemie. So we know that it's very important for us to study the molecules. Like if you know how molecules behave, if you know how, like it can help us in a lot of ways. For example, if I can go if you know that if I know guys, you guys, there's a at medium the principle where we study how this molecule behave, or this fluid behave in such a way that if I have a small opening and there is water in that small opening and there are larger opening, if I put little force on the small opening, it will translate that force to the particles of the molecules done in water. Then that force, it will increase according to the size of where it is going. So if the mouth is big, the force will increase, and that force is mostly used, like they use small force to rise, like to make big things, like to make larger things to rise, or to rise the other things. So we see the importance of molecules, and we see why is it important to study molecules. Something which is very important. If you study molecules, you will know you know how a gas behave, you know how liquid behave, you know all those things, you know how they behave. You can actually, if you study a gas, you can be able to create almost anything. Yeah, engineers, those who create planes, they take in consideration of the laws of gas or the laws of air. So the study of molecules is something which is actually very important. So une molécule est un groupe d'atomes qui conservent lors des changements d'état physique. So une molecule, it is a group of atoms which is conserved during the change of state physique, or which is, I can say, which is formed in such a, in other words, which is formed during the changement d'état physique in such a way that when I get hydrogen and oxygen, I add them together, I'll form a molecule which is H2O, NH3. If I get nitrogen and hydrogen, I bring them together, I form a molecule NH3. So these are different atoms. So if I get hydrogen, sulfur, oxygen, put them together, I form another molecule, H2SO4. So these are the molecules. So liaison chimique mostly under the réaction chimique, we talk about the molecules. Put this in mind. So, dans le chapitre précédent, on a vu comment les électrons sont répartis dans un atom. So, in the chapter which we are from doing, we saw how an electron is shared in an atom individually. Not an atom which is bonded, but an atom which is what? We are taking an atom on itself, hydrogen on itself, what? We saw how the electrons are shared, or how electrons are put in that atom. Then, maintenant, on va donc étudier la répartition des électrons dans les molécules et rechercher les causes de stability des molecules. So now we're going to study how these electrons are shared in a molecule when there's a bonding, a bond happens between molecules. How are these electrons shared? And we're going to search also for the stability of these molecules. And you know that when you share electrons, there's a way each atom shares an electron for it to reach stability. For example, I get oxygen. Oxygen has 8 electrons, which means my electron configuration is 1s2, 2s2, 2p4. So for me to have a balanced electron configuration, hydrogen, since we said the first shell is 2, is balanced already, then the second shell there's 2s2, 2s to the power 2, and 2p to the power 6. So 2 plus 2s to the power 2 and 2p to the power 4, which means if I add 2 plus 4 is 6. For it to be stable, I have to gain what? 2 electrons. So each atom has different ways. It's different from if I get carbon has 1s2, carbon has 6 protons or 6 electrons, which gives me when I'm writing this configuration 1s2, 2s2, and 2p2. So which means the first shell 1s2 is complete, 2s2 and 2p2. When I add 2 plus 2, it will give me 4. Meaning for carbon, it needs another 4 electrons for it to be stable. So it depends with the element or the atom. So we're going to study this. We're going to study how they share and how do they get each electron gain its stability. That's what we're going to study. So in fact, en effet, alors de la formation d'une réaction chimique, seul l'électron des valences interviennent pour distinguer different types of reactions chimiques. So, in fact, during the formation of the reaction chimique, only electrons of valency, electrons the valency, I mean the outermost shell, the electrons which are found in the outermost shell. So when I say electrons, the valency, I mean the electrons which are what? Found the reaction chimique. Électrons de valence, électrons trouvés à la périphérique, électrons trouvés à la couche externe. So, I mean the electrons which are found at the last shell. For example, I have 1s2, 2s2, 2p4. So what are the electrons found? These are the electrons which are found in the last shell. Since we said each shell must start with an S, so these are electrons 2 and 4. The electrons which are found in the last shell, and these electrons are the ones which will take part in this reaction chimique. These electrons are most of the electrons in the innermost shell who don't take part in the reaction chimique. For example, I get oxygen and the hydrogen. I want to bond these guys together. So when I bond these guys together, I see that only the electrons, the outermost electrons are 1, 2, 3, 4, 5, 6, which is the same as configuration. 2 plus 4 is 6. So there's 2, 2. Then electron of an hydrogen share they'll share and they'll give us something like this. So it will be 1, 2, 3, 4, 5, 6, 7, 8. You have seen it. 8 electrons is out here. It is balanced. And for hydrogen, 1, 2, it is balanced. 1, 2 is balanced. So these are the things which we know already. Oh. Yeah, so these are the yeah, I'm getting a complaint here that you guys you are tired. Yeah, I'm getting that you guys you are tired, and I can't continue if you guys are tired. It means we have to end from here. Yeah, even though I wanted to finish this thing, because I don't know if I'll be with you guys. Yeah, I don't know if I'll be with you guys. I wanted to finish liaison covariant. So I don't know, what can be your suggestion? I want to suggest something.
I think we can continue next week, Sunday, since you won't be taking us anymore.
Next week, Sunday? Ooh.
I agree.
Okay, then the problem is I'm having exam soon on 7th September. So, but I'll see what I'll do. Next Sunday, 16. Yeah, since it will only take us about 1 hour, it's not a big deal, since nothing which is something which is very little. Yeah, if you check something which is very little. So Sunday, same time?
Yes.
Okay, then Sunday I'll try explaining. Since if I continue, I know no one will get anything. I'll try on Sunday, or tomorrow. I heard tomorrow you are having a holiday tomorrow.
Yes.
Well, so that you it's a holiday for what? I'm not aware. Can you? It's a holiday for.
The boys will be playing soccer, so we're going to have a holiday because they'll go to Kenitra.
Or they'll be playing soccer at what time?
Most likely around 14.
I think 14.
So you even want to train or what?
Just a minute, Mr. Jacob. Mr. Jacob.
Yeah.
No, tomorrow's holiday, strictly no professor is supposed to teach. We are closed for good. So tomorrow, no professor is supposed to teach. So possibly on Tuesday we resume classes. So all classes that were scheduled for Monday have been cancelled.
Okay, then since I said no prof is supposed to teach, then Sunday's okay then.
Yeah, all right, Sunday is okay then. And then maybe I don't know how the timetable is for the guys, the engineers. I might have a class for Chimie General. Chimie General and Atomistique are almost the same. So I don't know how the timetable is. You guys that are doing Atomistique, you can still come and attend Chimie General because we're almost doing the same thing as you guys.
So you can teach them liaison chimique, right?
No. As in liaison chimique, you can go ahead with liaison chimique. Like maybe because where I am with the medical guys, I'm a bit behind with them. So maybe I might teach liaison chimique later on in the next school. So if you teach liaison chimique, it will be a bit okay for them, so that when I come for the second time, if it's going to come for the second time to teach liaison chimique with the medical guys, at least maybe it will facilitate their understanding. But right now, I've not even started doing what you call this, Approximation de Slater. I've not done configuration electronique with them. So next course I'll be doing is electronic configuration, règle de Krzyzewski, the hand, all those things. So it will be like the whole course will be based on how to do electron configurations, calculating Slater's energy, and later on in the next, because I can't do the same thing at the same day. Later on, maybe that's when we can go into the Chimie, which will be the next week, which will be the following week. Because tomorrow I was supposed to have Chimie General. I would have done that tomorrow. Then on Thursday I would have done the Chimie, but now because we don't have class tomorrow, so the course for Monday will be moved to Tuesday. So no, Thursday. Then the Chimie that other week probably. So it's okay. It's actually okay if you just teach them on Sunday. So that even when I come on Monday, I just finish up with everything, because I told the guys for medicine to actually attend this class as well. Yeah.
Okay then.
Yeah.
So on Sunday we'll create something. Yeah. And I'll try sending some questions for you guys, so that you try writing some configuration, all that, and yeah, then on Sunday, I know it will only take me about 1 hour, 1 hour or 30 minutes, so I'll be done with the topic. So on Sunday, I will see what I can do. Just for 1 hour, I'll teach you, and we are done with it. The whole topic for Atomistique, and you'll be well. You'll be well with everything Atomistique. Yeah. So have a blessed evening. Yeah. And thank you for participation.
Thank you.
Thank you too.
Thank you.